Okay, so we're going to have to do this on 3 different computers, of course, but whatever. Made it this far. Hold on 1 second. Discussion. Okay, so before doing the stuff from the reading, I want to talk some about the homework. Homework here, homework there, homework everywhere. Okay, so the first question is based on this paper by 3 political scientists. So fortunately, you can get their data, and you could have done exactly replicated what they have done, but we wanted to do it in a little bit more of a Bayesian way. So that can be done with BRMS. So here's code there at the bottom to do it. Basically, you can create a spline variable, and one thing that I guess I might not have talked about last time is that you can stratify, essentially, splines, which are continuous by a discrete factor. So in this case, the factor just has 2 levels. Left plurality is true if the left party has more votes than any other party, and false otherwise. But in general, this could be any sort of a factor. So you could estimate 1 spline for each state, or you could estimate a different spline for each race or something like that. And so you can have the way an outcome or the log odds or whatever responds to a continuous function vary according to categorical characteristics. And that can be extraordinarily useful, particularly in a Bayesian context where it actually works. Because when you stratify by a categorical variable, it's still going to have the prior structure of it with, Bayesian version of hierarchical models pooling toward a central continuous function. And so, like, if you estimate 1 spline for each state, it's going to pool toward, like, a population average spline. And that's going to require strong evidence within a state in order to deviate substantially from that. So in this case, you sort of have partial pooling toward a continuous function, and that's really what makes hierarchical models work well. So we've got the rest of that code here. It runs, and then as usual with splines, you can't really just look at the parameters and be able to tell what's going on, so it's best to make plots. Kind of unfortunately, this first plot here is not useful. So remember, I said on the thing that when BRMS does these splines, it pulls the linear basis function out from all the rest of the stuff. And so the linear basis function has its own coefficient, and that I think is a little bit dubious, but it allows someone who basically was just like, I want to just interpret the linear part of this, and the nonlinear part of it is just like noise that I don't even want to deal with. That you could look at the coefficient of that. However, when it makes the plot, so this first plot is of the linear basis function. By construction, the linear basis function is linear. So this is not any empirical evidence for the proposition that the outcome is linearly related to the running variable, in this case, left plurality percentage. This is the linear part of a nonlinear function. So the only thing really that this tells you is that this line has a slope, and it's slightly positive. So the linear part of like 10 or more basis functions has a slightly positive slope to it, but that doesn't tell you anything about the nonlinear parts of it. The second plot is closer to useful. So this shows the difference in the expected outcome, or the level of the expected outcome, for if the left has the most seeds or not. But this second plot is based on the average value of left plurality percentage by default. Like if you don't specify anything, it just sets the variables to their averages, the other variables not being plotted here. So the average in the data of left plurality percentage is close to 0, but it's not exactly 0. So the second plot almost tells you what you want to know, but not quite. So that's that one there. The third plot is actually closer to useful. So this shows the interaction between the two variables, the running variable and the dichotomous variable, as to whether it crosses. So the red function there is conditional on all the data where left plurality percentage is negative, but it's extended across the whole range. And conversely, the blue function is estimated on all the data where left plurality percentage is positive, but it is also extended farther to where the values are negative. So the difference between the red and the blue function is what the authors are trying to get at with this regression discontinuity estimator. Well, their regression discontinuity estimator of the causal effect of the left party having the first opportunity to try to form a coalition if they don't have an absolute majority, to nominate the prime minister and start doing policies and stuff. So the difference between the blue and the red function is relevant, although in order to actually compute the numbers of it and stuff, you need to either plot or just summarize the difference between these two functions at 0 rather than the levels of the function. But it does appear as if the blue function is slightly larger than the red function. You can also do a better version of the second plot if you just make a tibble with left plurality percentage exactly 0 and then plot specifically the effect of left plurality given that the left plurality percentage is 0, so they tie. So that looks like this, which pretty much looks the same as that. But this one is slightly more correct. But like I said, this plot here, in order to really do the analysis that is along the lines of what's in the paper, you need to call posterior EPRED with a tibble that has two columns, both of which, the first column is constant, we're just going to set that to 0, and then the second column is whether the left has a plurality or not. So we're looking right at the threshold. This is why they refer to that as a local average treatment effect. We're talking about the causal effect of essentially going from almost having a plurality to just barely having a plurality. And when we plot that, looks like this. So just by looking at it, we can see, more likely to be positive than negative, unlikely to be huge, maybe longer right tail than left tail, all sorts of things like that. So that plot is pretty useful. But we could actually calculate some specific numbers and, roughly speaking, compare that to those in the paper, keeping in mind that the paper uses frequentist estimation methods. So it uses frequentist estimation method. It's fairly common for political science, but reading the paper, they just kind of go through the motions. Like, they do say some stuff is like significant or not significant or whatever, but they're not really leaning that hard into frequentist analysis. Moreover, they don't have a sample. They have essentially all observations for which we can get data on what happens when there's like a close election in a parliamentary thing with not too many parties. Like, every time that has happened in recent history, they have data on. So there's really no frequentist question that can properly be asked here. We're back into the realm of like, is X composite or prime? There's no sample here. We essentially have the population of the past events that fall into this category. And so it would be entirely reasonable, even though the authors don't really do that, to make the analysis conditional on these historical episodes, in which case it would be Bayesian. But, they don't do that. So if we were to summarize the difference between the mean or the expectation when the left party has a plurality versus when they don't, we get a median that is about 0.04. So that is much smaller than the point estimate that was obtained in the paper. We get a 95% credible interval that ranges from about negative 0.08 up to about positive 0.2. And so this 95% credible interval has a width of less than 0.3, as compared to the 95% confidence interval in the paper, which goes from negative 0.01 to like 1.19, so a width of 1.2. So basically speaking, their 95% confidence interval is 4 times as wide as our 95% credible interval, which illustrates why it's important to distinguish a CI, whether you're talking about a credible interval or a confidence interval, because they are estimating different things, even if people insist on interpreting them the same way, which is a misinterpretation of a confidence interval. So the misinterpretation of a confidence interval is the correct interpretation of a credible interval if you actually do the Bayesian analysis and stuff. Moreover, we can compute the probability that the causal effect is positive, who get like 0.724, and that's reasonably important, reasonably useful. That is not something that can be coherently said or estimated from a frequentist perspective, because this is just, similar as saying, is beta positive? That's a property of beta. So from a frequentist perspective, that's either true or false. We don't know which. But the beta, or the causal effect here, is not a random variable, so it doesn't make any sense to say it's probably positive or probably small or anything having to do with probability if the thing you're talking about is not a random variable. But from a Bayesian perspective, we don't know exactly what this causal effect is, even though we have a whole bunch of historical data. but we can say our beliefs about it are such that the probability is positive is about 0.72, or if we want to be more particular about it, 72% of the 4,000 posterior draws of this were positive. So even right there, I would argue that the Bayesian version of this is better than the frequentist version of this. Now, it yields a smaller estimate of posterior median, so the authors might not be real happy about that, but the credible interval is narrower. We're able to say the probability that it's positive, things like that. Moreover, like I said, there's really no frequentist question to be answered here because we don't have a sample. So it's false to say if we were to repeat this study an infinite number of times, the average of the point estimates would be equal to the true causal effect. It's also false to say if we were to repeat this study an infinite number of times, the proportion of times where we get a point estimate or the proportion of times that the confidence interval estimator fails to include the true estimate will only be 5%. The reason why both of those statements are false is because it's impossible to repeat this study with a different sample of data because we don't have a sample of data to begin with. If someone were to repeat this study, they would be using literally the same observations plus maybe a couple more observations from the future. So it doesn't really make sense to talk about the proportion of times that something would or would not happen if we were to repeat this study over and over and over again with different random samples when that is not something that is feasible to do. Which is why I would say it makes more sense, and probably most of your audience would just kind of automatically default to this way, to consider the analysis conditional on these data rather than marginalizing over hypothetical samples of them, in which case it's a Bayesian analysis. So because we don't have a sample here, the bias correction and the confidence intervals and stuff that this RD robust function are returning don't make sense. But that doesn't mean that they are wrong, in a manner of speaking. So when people publish papers about the properties of this estimator, write a R package that implements some stuff like this, they're like, well, under the assumption that you have a simple random sample, blah, 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 blah. And if somebody like the authors of this paper wants to come along and apply the estimator to data that is not a simple random sample, in which case the confidence interval and the bias correction and all sorts of stuff like that don't make sense, well, that's their fault, not ours. Right? That's the fault of the people who are applying to the paper when they don't have a sample, rather than the people who derived the estimator and wrote the R package. So there's a lot of that kind of goes on where people will derive an estimator, write it up in an R package or whatever, but they're like, well, we're not responsible for the people who misuse it, and we're not going to really make any effort to encourage people to do things the right way. And you see that a lot with frequentist stuff, even going back decades. They're extremely hard line on Bayesians in terms of the subjectivity to the prior or whatnot. But they're like, well, if people come along and they use frequentist estimators and they misinterpret the confidence interval and they can't define what a p-value is and they do all sorts of other nonsense, well, blame them, not us. But that doesn't yield a particularly healthy scientific development of knowledge. And so that's, probably not great as well. In addition, or last thing here is that the estimator used in the paper and the default one in this RD robust package assumes that the function is linear on both sides of the discontinuity. So it has the same slope on both sides, but it has this jump at 0 as a result of that. So the Bayesian way we're able to do that relax the assumption. Wait, what happened? Simultaneously fell apart. Okay. Relax the assumption that all this stuff is linear, when really we have no theoretical reason, and almost it's very hard to come up with an example where we would have any theoretical reason to believe this relationship is entirely linear. So, with the Bayesian thing, we're able to relax that assumption. We're able to include prior information that this function is unlikely to be exactly linear, but it's also unlikely to be super nonlinear function. And, do all the stuff that we do and get, I think, better or at least more useful, by better I mean more useful quantities that come out with it. Okay, so any questions about that so far? All right. Moreover, since we're Bayesian, we can get Pareto K estimates, which indicate the sensitivity of the posterior distribution to particular observations. Now, in this case, observation 10 has the Pareto K estimate that is way too big. So this, technically speaking, invalidates the estimator of the ELPD. We could fix that relatively easily if we wanted to. It does not, theoretically speaking, invalidate the posterior distribution. It just means the posterior distribution might be or is fairly sensitive to this one observation, and so when that happens, it's definitely good to look at that one observation to see, what's going on with that. It turns out to be New Zealand in 1984. So I don't know a whole lot about this, but I looked it up on Wikipedia. And as it turns out, the Prime Minister went on television to announce there would be an election in a month, but he was drunk when he went on television, and so the election did not go so good for his party. So he was in the Conservative Party, and then he was drunk and decided to call for an election. And then the Labour Party won an outright majority of the seats in New Zealand. And so this is kind of exactly the situation that the authors are interested in. The Labour Party was just before 1984 was just barely the second biggest party, and then they had the election and they got the majority of the seats. And so then the question is, well, how does the international bond market react to an event like that when the Conservative Party, essentially loses all power, and now the Labour Party gets to implement its policies, at least until the next election. And, there could be some concern in the bond markets that, the Labour Party, for New Zealand, there's probably not risk that they would just not pay the bonds back, but they could pay the bonds back in New Zealand currency after a whole bunch of inflation. If they spend a whole lot and don't raise taxes to pay for it, have budget deficits, have more inflation or whatever, they might be paying these bonds back with currency that has less purchasing power than when the bonds were originally issued or whatever. And that could cause bondholders to demand, higher prices, sorts of things like that. So if we were to do a case study, we could say, well, this might be exactly the case to think about, or one of them. So in that sense, it's kind of, this sort of scenario is what the paper is talking about. However, the Labour Party won like a big majority, and so this one observation actually gets thrown out by the RD robust estimator in the paper, which uses this bandwidth thing to decide how far in both directions the estimator should include observations for estimating the slopes of this deal. Anyway, so this 0.2 is outside the bandwidth that it found of 0.14. So the paper actually is not influenced at all by New Zealand in 1984, but it's telling us that our estimate is pretty sensitive to this one observations because we're not messing with bandwidth or anything like that. So it's at least something to look for, and it would be easy enough to just re-estimate your model without that one observation, see how much the results change, in which case they would be like even smaller estimate of the posterior median without that one observation. But anyway, so it doesn't mean the posterior is wrong. It just sort of means our beliefs about what they're talking about here with this causal effect are, unusually, atypically sensitive to this one historical episode. And, we might not want to make sweeping conclusions about bond markets in general or parliamentary democracies in general on the basis of one election in 1 year in a country that has more sheep than it has people, and no economy to speak of. They have an economy, but it makes no difference to world. So you don't really want our conclusions to be overly sensitive to what may be an exceptional situation. Okay, so questions about that? Right. So I think that would be another example of the advantages of Bayesian approach to something like this. Also, it should be said that the paper by Ornstein and Hayes and Francis, it's example of modern, but run-of-the-mill political science research. And so, as we were talking a little bit about the first day, but it might not have been something you really appreciate the first day, when you get beyond sort of the toy stuff that you learn in introductory classes, like how to do a t-test of a difference in means or whatever, to start using the estimators or things like the estimators that social science researchers are using for social science research. Well, one, the frequentist estimators get rather complicated. Not complicated to use. The RD robust function is I guess pretty easy to use. But what the asymptotic distribution of the estimator across possible data sets is can be a complicated thing. And this bias correction to it, that's another complicated thing. And so these frequentist estimators, if you sort of take them seriously, that are used in actual research are much more complicated than the frequentist estimators that you sort of learn when you're doing an introductory class. Moreover, in situations like this, we almost never know the finite sample distribution of stuff. We only know the asymptotic distribution. And it's not cheating, but it's kind of a cop-out. One, like it's completely ridiculous to complain about priors in a Bayesian analysis and then say, well, we're going to analyze our frequentist estimator as n goes to infinity. Because as n goes to infinity, the prior wouldn't have mattered. So they're sort of saying, well, in a situation where the prior doesn't matter, here's the property of the estimators. But moreover, like in any actual situation, we're going to have a finite amount of data, not an infinite amount of data. And how close the distribution of the estimator is to its asymptotic approximation when you have some finite amount of data. In this case, like 150 or something observations to start with. It may or may not be that close. Moreover, all these asymptotic approximations, like as n goes to infinity or whatever, when n is finite, the distribution of the estimator depends on population characteristics that you don't know and you're trying to estimate. So you don't know if your estimator is going to work well enough on that population if it has a finite number of data points. Like it could give you estimates of the population parameters that make it look like the population is more amenable to the estimator than it actually is. And so, when you're doing this with a small number of observations, you really don't know what the distribution of the estimator is across data sets of size 200. Or you have to do a ton of simulations in order to figure it out for like all sorts of different situations that the population could be. So anyway, it gets rather complicated to do frequentist stuff well, even if you were so inclined. In contrast, with the Bayesian stuff, well, it's also complicated. We had to do a lot of stuff like just to get to the midterm. In terms of learning about probability and like how the Bayesian stuff is different and working with distributions rather than just numbers and like MCMC and physics and all this other stuff. But once you get like kind of comfortable with that or learn that decently well, then it doesn't get a whole lot more complicated. Like the stuff that we've been doing after spring break, we're just adding like a little bit of complication each week. But we're still using the same estimator. We don't have to rederive that or have like a different MCMC for each situation that we might have. Like we didn't have to have a different HMC to do this regression discontinuity thing, whereas in this case they had to derive a whole different frequentist estimator. So I think those are all reasons why I certainly would have preferred had the authors done a Bayesian approach to this, but I'm not surprised that they didn't. Mostly because there's very little Bayesian stuff in political science, but in particular, the causal inference literature is especially influenced by point estimator people, even if they don't really like believe that they have a sample or stuff like that. So anyway, no real surprise. Next question is about this blog post or sequence, or it's like a whole section of Gelman's blog as to why he hates regression discontinuity papers, or more specifically, hating regression discontinuity papers that the only thing that they adjust for is the running variable, or the in this case left party percentage. So how did you all think the authors would have responded to that criticism? How do you think it should be done? The sorts of questions that were asked about there. What did you think about that? Anybody think?
did try to adjust for the sensitivity of the functional form, right? And I forgot the exact name of it, but I know they used the CCT method. And they also did a series of balance tests, so they did try to adjust for the fact that, well, I guess to his criticism that a lot of people, or a lot of authors, don't actually do any, nor the pre-treatment variables, so they try to adjust for that. I mean, in terms of, they did acknowledge the limitations, but I guess they didn't acknowledge other ways that could have been done, so maybe Gilman would have drilled them on that, but those are kind of my thoughts on it.
Yeah, so in a section in the main text of the paper, they were like, here's some other variables, and we need to show that these are continuous around the threshold of 0. And they had like a plot, and there would be like little gaps in some of the variables around 0, which would suggest they aren't continuous. But then they were like, well, most of these little gaps are not statistically significant, except for one of them, and the one of them doesn't make sense. So, like, blah, blah, blah. So that is, I think, not in response to Gilman specifically, but in response to the idea, well, it's an observational study, so you need to consider other variables, but the way in which they decided, these other variables don't make much of a difference around the threshold because these little gaps are not statistically significant, is not something that Gilman or really anybody would say is a good way to make that determination. Now, also in the appendix, they did use an even more complicated estimator that allows for covariates, and they put those same things in. So I think the others are not really unaware that these sorts of criticisms are out there. So how do you think would have been the best way to approach the idea of estimating this causal effect?
BRMs, right?
Well, yeah. I mean, obviously.
Is that like an interaction term, maybe? Or just a nice simple regression with an interaction term instead of doing the splines method?
Possibly, if you had enough reason to believe that relationship was linear. I think, like in most cases in social science, it's sort of in a gray area. We don't have any strong reason to believe that it's linear, but we don't exactly know like why it would be nonlinear. So a lot of people like this paper would say, well, you're in that situation, just estimate like linear on both sides of it. Whereas the Bayesian way of thinking about it would be like, well, if you don't know it's linear, then you should put a prior on how nonlinear it is, maybe probably not that much, and then update your beliefs about that. And, you might get a plot that looks, something like this or whatever. And it's like, well, the blue one is like not totally linear, but maybe kind of. So yeah, you can do some stuff like that. What I thought in particular was, at least according to Gilman, you would want to include these other variables, even though I'm not really sure why the levels of these variables would explain the change in the month after the election to the month before the election in the bond market stuff. But, okay, if those are the variables you think might make a difference, might as well include them. I thought it would be prudent to maybe relax the likelihood to be student T rather than Gaussian. Do like we did last homework, estimate the degrees of freedom, to allow maybe some heavy tails in the error term for these situations like New Zealand, which in 1984, which was way different, maybe. Also, the authors, toward the end of it, they make this argument, well, the magnitude of the causal effect should depend on how far left the left party is relative to the right party. And so that is another continuous thing that can be quantified with ideology scores. And one of the good things about splines that really can't be done with any of these RD robust packages or whatever, we can estimate a bivariate continuous function of left party percentage and the ideal point difference between the left and the right party. We can even estimate multivariate functions that have more continuous variables than 2. You would not want to do that without prior information that, these functions probably don't differ from each other too much. But you can certainly do that in BRM or RCNRM. Going to need proper priors on stuff. Probably, not under your prior, the standard deviations going into it, probably not that big, but we could do it. And I think that would have been better and a better way to substantiate this hypothesis that, if the two parties are really far apart, then it's going to have a bigger effect when the left party surprisingly wins an election than if the two parties are pretty close together to begin with, in which case, does it really matter who wins? They're probably going to coalition with each other anyway. So things like that. Okay, so criticism. Any other questions about the regression discontinuity thing? So then this pulse data set is kind of interesting. It came out every 2 weeks for a while, and then they discontinued it because they ran out of money. But during the pandemic, they did have money. So, you can download any particular week. This was the first week that they did it we were looking at. And we wanted to estimate. Oh, question?
Yeah. So with that data set, was this data separate from the census data then that came out in 2020?
Yes.
Okay. Cool.
So the census thing. Okay. There's a Census Bureau, and their primary function is to do the census every 10 years. But the Census Bureau produces other data sets besides the census, and this Pulse thing was one of them. Also, the census is not a survey, or it's not a sample, even though they make 5% of the census data available as a sample. So anyway, this is a separate thing, and it's not even nationally representative. We'll talk about that in a second. But anyway, so you could do different models. There's all kinds of questions and predictors. I did one about food security. So like I said on Ed discussion, can make this go a little bit faster in situations which is fairly common in the social sciences where all of the predictors are categorical. Then you can count up the number of times each thing happens, use that as a weight, and then you have much fewer unique observations than you have total observations. So I did answer the question, how much food security do you have based on sex and based on race, using the monotonic construction for education. So what's the highest level of education you have, and what was your annual income in the 2019 or something like that. Also allowing the coefficient on state to vary from one state to the next. And so usually if you have a geographical variable in the data, you would want to use it. I think in particular it makes sense because people who live in different states were being subject to different state policies in terms of whether there was lockdowns and stuff like that. Also, different states were subject to different intensity of the pandemic. So, at that time. So those could both be reasons why we would want to allow the intercept to vary by state. And as we can see in the posterior distribution, the the mean of the standard deviation across states was 0.17. So that doesn't sound particularly huge, but it's certainly not zero. If it were zero, that would basically means there's no heterogeneity across states. But in the United States, there's always heterogeneity across states. Actually, pretty much any country that has like states or provinces or whatever, there's going to be a lot of heterogeneity across states. So like Canada, Switzerland, all that. And then, we get summaries of the draws here. White people had much more food security than the non-white races. And unsurprisingly, the posterior mean of the direction of the educ and the income variable, both positive, so more income you have, more education you have, expected to have higher degree of food security. No real surprise there. But just talking about this in terms of like log odds is probably not the most effective way to convey your results. So much better to use a plot like this. So it's showing how the probability of you answering the 4 different categories of food security varies as a function of education. And this is going to hold the other variables at their means by default. I could have gone in there and specified the means, or specified what values to evaluate this as, but I just used the defaults for it. If we had multiple models, or if you wanted to estimate multiple models, you could use Lu to compare them. Seems like it comes out fine in this case for me. I think it did not totally come out fine for everybody, and that is attributable to the fact that we were using grouped data. So if you use grouped data, then the leave one out concept says, what if we were to leave out one stratum? And if your stratums are sufficiently large and you left out one of them, then that would have a noticeable effect on the posterior distribution. If you stratify by state, then the strata are like, I think, sufficiently small that you didn't run into this problem, and maybe some other people did. It is easy enough to fix or work around that if necessary. Also, you could have made predictions, and like this is something that a particular state experiencing a pandemic and a lockdown and all that might actually be interested in predicting, like how much of a food security problem would we be having in New York or whatever the other state you might be interested in which case you run into the problem that the pulse survey, like I said before, is in no way, shape, or form nationally representative. So usually when the government does a survey, they'll at least try as best they can to make it nationally representative. Obviously, the census is intended to be a count, although they miscount. And anyway, but we're not going to get into that. But this one was administered online, and the turnaround time for this survey was much shorter than a typical government survey, where they have to do a whole lot of work in order to get the sample to be representative of the population, or at least to try. So if you just look at these data, it's like 80% white respondents, although they don't distinguish, or they count Hispanic as part of white, the Census Bureau does, or they ask the question about, are you Hispanic, but that's considered ethnicity rather than race. Anyway, it's complicated. But also, like 60% of the respondents were female. Like that's obviously not proportional in the population. And from a frequentist perspective, this is pretty much a disaster in terms of trying to infer something about a population from a sample that is like not a simple random sample from that population. If it were a simple random sample from the population, we wouldn't have these distortions. But from a Bayesian perspective, it's not actually that big a deal, provided that the people in the data set are representative of the people that have the same demographics in the population. So if the only problem is like, okay, it's 60% female and almost 40% male or whatever, as long as the female and male people in the survey are representative of female and male people in the population, we can deal with it if the only thing we have is like it's supposed to be 50-50 and actually is 60-40. So by that I'm talking about post-stratification. So if you make predictions on the basis of this model, which is conditional on the data in the sample, and you know in the population that it's like supposed to be 50% men and 50% women, basically, then you can make predictions with new data being like every possible stratum that you have in the population, and then weight those predictions by the proportion that you know to be true from the census. And so that's what's called post-stratification. And that is another big advantage of the Bayesian approach there, to be able to straighten out these sorts of things. And, having some lack of representativeness in a sample is actually the norm rather than the exception. This is pretty extreme, but it's something that in general you're pretty much always going to have to face anytime you have a survey data set, which are very common in the social science, but always have to remember those surveys are not simple random samples from a population. Even if they're trying to be representative, much more likely to use cluster sampling or stratified sampling or all sorts of other things, which makes life very complicated if you want to take a frequentist approach, because how you collect the sample affects the distribution of the estimator. It's not really all that complicated from Bayesian perspective, because you're conditioning on the data, and then if you want to make inferences about population, you just use the population proportions rather than the proportions in the data that you observe. Okay, questions about the pulse question? Yeah?
It's shown ELPD of negative 65,000. That would imply that your model's really not that good at making new predictions.
No. So ELPD can only be interpreted in relative sense.
Oh, so just compared to another model.
So I didn't do another model, but it would only be useful in the difference between those two. And, okay, it looks like negative 66,000 is horrible, but we have to keep in mind that that number is based on what if we were to have a future sample of size n from the same population. And because we have the huge numbers here, n is huge, and so anyway, those should only be interpreted in relative terms. All right, so last question was about jury selection, maybe more generally, but came up with a question based on jury selection that happened to be going on in Manhattan as we speak, or at least last week it was going on. Now they have a jury, and hopefully they can actually get to the end of the trial with that jury. So what do you all think about the idea of taking a Bayesian perspective on what juries and lawyers and stuff like that are doing in a criminal trial? Yeah.
So I thought using Bayesian methods would be kind of important, just because I was definitely thinking about this, because I think Trump was trying to get rid of one of the juries one of the jurors because they have ties of anti-Trump and all of that. So basically why I bring that up is because some of these people come in with preconceived notions, Donald Trump is a very prominent figure and he's well known and people probably already have like previous opinions on him, but then they have to listen to the evidence that the court gives to kind of make that decision whether he should be guilty or not. So I thought this was like a really cool like way to apply Bayesian methods to this, because I feel like people might just stick with their priors, but I mean, who knows, maybe there might be some who will like listen to the evidence and maybe kind of change their initial thought that they had.
Right. So I think if you sort of think about this as like a game theory thing or a formal theory thing, then it's probably a pretty strong assumption, or it'd be really just absurd to think a juror is actually calculating stuff with Bayes' rule. But as a theoretical device, or to say like they should be behaving this way, or like when the lawyers are deciding who to strike, maybe they're using game theory sorts of ideas. Like, all that would be fine. All that would be typical for economic research, legal research, etc. And it goes back to this kind of weird thing where, like, in game theory, it's totally obvious that the game is about people using subjective probability, and they, like, update them. And there's, like, all kinds of complicated game theory stuff out there. But then when it comes to, like, econometrics or statistics or estimating parameters of this thing, they're like, no, we can't use Bayesian methods. That would be subjective. So that is, like, discordant. But yeah, we certainly have this idea that jurors are making decisions about the outcome, and prosecutors are making decisions about strategy, and so decision theory with subjective probability seems like it might be something that would be applicable. But at the same time, it doesn't seem like judges would be real happy if there was like a Bayesian prospective juror. So they kind of say stuff to the effect, well, you should put like all your prior beliefs and stuff aside, only look at the evidence that is introduced in the case or in the court. Which is probably not really possible to achieve, but it's also unclear, like, what would it mean mathematically for someone to have, like, no prior information, particularly in a situation like this, with Trump. But what do you think would be the most appropriate uninformative but proper, or uninformative, maybe including improper, prior for a juror to have in a criminal case? So Wikipedia talked about like 3 different senses in which you could have a uninformative beta prior, all of which convey some information. What did you all think about that?
I thought just regaining the name of it, what the one where the base of the cross prior has a beta 1-1, because I remember reading from the textbook in chapter 4 that French is just going to converge. Your posterior is going to be exactly the same as your likelihood, so you're just going to base all of your beliefs on the evidence presented. So that'd be the ideal. Right. So the 1-1 prior, yeah. So it's going to be flat. So it's a uniform distribution. Right. But so that is usually when we think about uninformative prior, we're thinking about, well, what's the prior that's either totally flat or the most flat possible. So that is certainly something that is used a lot in research, but if you read the Wikipedia thing, it's actually pretty long. They sort of say, well, that 1-1 prior, like the posterior distribution is going to be data plus 1, or A star and B star are going to have this like plus 1 business in each of them. So that conveys the prior information that both events are possible. And that might say, okay, well, that makes sense. Like, he could get found guilty or he could be found not guilty. But
is it possible for the same defendant to be both guilty or not guilty, as compared to what I think Wikipedia called the Haldane prior, which is let A and B approach 0 at the same rate, which basically says there's a prior probability that he's guilty of 0.5, but it could be the case that the truth is he's like totally guilty or totally innocent. So not taking a position as to which of those two might be a priori, I think that is closest to what I think judges are looking for, but it's kind of hard to say because judges have no idea about base rule or whatever. But anyway, that is the improper prior, which is to say it's not uniform on the 0-1 interval, it's uniform on the log odds. And then there's another prior, Jeffries, which is kind of in between those two. I don't exactly think it makes sense in the context of a criminal trial, but it conveys the same amount of information no matter what transformations you do. So a lot of people think that in a lot of circumstances is reasonable because they don't think the transformation should really be like influencing anything. So anyway, it could definitely say different things there, use decision theory in different ways. But yeah, we'll have to see how that goes. And then the last part of that question, well, how do you think, what sort of priors would you choose for how the result of the New York trial might affect the election? So what did you all think about that one? Yeah.
I mean, there's like so many different court cases, so I feel like it's kind of like
yeah. So this one seems like it might be the only one that actually finishes before the election. But anyway, I guess you could give a different answer for different cases, maybe.
Yeah, because it also would depend on the charges, right? Because I know with this particular case he's in trial for, like even there's been some people like, why is there like a trial for this that makes like everything else kind of look like, oh, a witch hunt or whatever, from some of the stuff I've heard from the pundits. So, and then I also just think that like, there's been a lot of like uncertain events kind of happening in our politics. So, like maybe if something happens at the convention, like for both, or so just something like that, or something international happens that could also kind of have an impact on what that might look like.
Right. Yeah, I think definitely you have to have, if you're going to do some sort of model for this, interaction between the results of a trial, whether it's this one or one of the other ones, and the characteristic of the voter. So certainly you have many strong partisans both ways, that I don't think the outcome of the trial is really going to change the fact that they're strong partisan. And kind of one of the defining things about the United States right now is that there's like very few people who are not strong partisans. But to them, something like a criminal trial might make a little bit of a bigger difference. So you would want to have interactions, and you would probably want to have priors on the effect that are rather small. At least for this trial, which is, like it said, pundits or whatever, even like legal pundits are sort of describing this one as like kind of a technicality, like fraudulent payment receipts in order to commit election fraud or some sort of thing, as opposed to, attempted a coup or took contingency plans for the United States invading Iran to your house, which, could be more consequential sorts of crimes, maybe affect people's beliefs more, etc. But anyway, another useful application of subjective probability. Okay, so now if I can, what am I on? Okay, so turning to what we're supposed to talk about today, which is still on hierarchical models. We still got to say this, although it occurred to me that perhaps I should have said somewhere before the last week of the semester, this particular thing here was put in place long before Manish Shafriq took over. So this has nothing to do with that. Just let you know. All right. So the reading, Mikhail Reed talked about two-stage least squared, which is an estimator for instrumental variables. Very common in economics. This is probably, if you were to pick one like quantitative method estimator that is native to the social sciences, it would be instrumental variables, even though this is now used in like biology and stuff like that as well. So two-stage least squares is an estimator. First stage, you predict the causal variable with all the other predictors, including the instrument. And then you use the fitting values of the first stage in place of the causal variable, model the outcome with the fitted values and all the predictors except the instruments, get a point estimator of the causal effect. And the main thing to keep in mind is that two-stage least squares is not even a good estimator on frequentist, from a frequentist perspective. So it's not a good estimator. It can be good, or it can be real bad, depending on the population and how large your sample is, assuming you have a sample in the first place. But it's finite sample behavior because it depends on characteristics of the population, and we don't really know those characteristics of the population. And if it's like the population is such that the estimator is not good, we might not be able to tell that because the adverse nature of the population is adversely affecting the estimator in the first stage. But some of you have had classes on this, but just kind of quick review, and hopefully this is simple enough that even if you hadn't had a class on this previously, can follow along. So this is a simpler case than the reading, but let's say we have a treatment variable x that's binary, an instrument z that is also binary, an outcome that's like continuous y. Then the instrumental variable's point estimator can be written as the ratio of the covariance between z and y divided by the covariance between z and x. And the two-stage least squares estimator and the less commonly used full information maximum likelihood estimator are equivalent to this estimator under the conditions that like x is binary, z is binary, nothing else is going on. In the more general case that people are going to mostly use two-stage least squares, but this simple case is already, I think, illustrative because, okay, both the numerator and the denominator are covariances, and we have covariance point estimators that are asymptotically normal across randomly sampled data sets. And we've already seen, although it was a long time ago, so you may have forgotten, but the ratio of two normal random variables was on like Wikipedia, it's PDF or whatever. But if you have a ratio and the denominator can either be positive or negative or arbitrarily close to zero, well, if you take something and divide it by something that's arbitrarily close to zero, you can get an arbitrarily large ratio. And that's the fundamental reason why this estimator or the ratio of normals thing is so heavy-tailed, it doesn't even have an expectation. Like the integral defining the expectation diverges rather than yields area. So this estimator, full information maximum likelihood, doesn't have an expectation either. Two-stage least squares only has expectation if it's over-identified, which is to say you have more instrumental variables than you have endogenous variables that you're trying to instrument. Usually you just have one of each, in which case two-stage least squares doesn't have an expectation either. So the reason why I say this is a bad estimator on frequentist grounds is that in finite samples, it's so heavy-tailed that it doesn't even have an expectation. And so there's like a little bit of probability on preposterously large estimates. Could be positive, could be negative, like both directions. And that is particularly going to be a concern when the covariance between the instrument and the treatment variable is close to zero, which is the situation that's referred to as a so-called weak instrument. And there's been a lot of research, about that and other things. So in the case where you have a strong instrument, then this estimator, like at least on frequentist grounds, can be rather good. But you don't know the true population denominator. You have to estimate it, and the estimation is subject to noise, particularly if you have small samples, and things can go badly off the rails. So what does a generative model look like? Possibly approach this from a Bayesian perspective. So we're going to model the treatment variable and the outcome as bivariate normal. And so we got all these parameters, and they're going to have priors. The linear predictor for the first one, which is for the treatment variable, it's going to depend on z, which I'm calling the instrument, in addition to x. And so z has a coefficient which I call zeta, that from a Bayesian perspective you're going to need to have a prior on. And from an instrumental variable's perspective, it's important that the relationship between z and mu1 be monotonic. And of course, when most people say, it's got to be monotonic, they just assume it's linear. But linear is only one form of it being monotonic, and the relationship might not be linear, but it has to be monotonic for the instrumental variables thing to make sense. And then you have a second linear predictor for the outcome, and that's going to depend on an intercept, obviously, and it depends on x, but not z, and not t. So that's where this whole idea of an exclusion restriction comes in. And then you need to have priors on the parameters that go into the other part of the model as well. So main thing to keep in mind here is that if t and y are distributed bivariate normal, then the conditional distribution of y given t, we've talked about a couple times, is going to be univariate normal with expectation that's shifted over by the ratio of the standard deviation of the outcome to the standard deviation of the treatment times the correlation between the errors times the difference between the treatment and its expectation. And similarly, the conditional standard deviation is going to be scaled down by the square root of 1 minus rho squared. And in that situation, how does the expectation of y conditional on t differ from the marginal expectation? Well, the causal effect is going to be this ratio of sigma of the outcome to sigma of the treatment multiplied by rho. And so those three things together are going to constitute the causal effect that we're interested in trying to estimate. And so you're going to need priors. Could very well restrict the sign of the correlation. So usually there would be some theory as to whether the correlation of the errors would be like positive or negative. Here I just let it be uniform between -1 and 1, which is also maybe okay, but maybe not as informative as we could be. like I was saying, two-stage least squares, it's not super complicated, but it's more complicated than least squares. Like you have to learn a different estimator in order to do this thing. Whereas, Bayesian stuff, Stan, MCMC, we just kind of do our thing, follow the generative model. And then once you have posterior draws of these three things, you can combine them together and you get a posterior distribution of delta, the causal effect that you are trying to estimate. And so this is illustrated in the reading of McElroy's reading, going back a long way to this paper by Engres and Kruger. Get the data. So this is based on this idea that different states at different points in time had different rules about when you're allowed to start first grade and when you're allowed to drop out of high school. So a lot of states had some rule, like you have to be 6 years old to start first grade, and you're not allowed to drop out until you're 16. But if you turn 16 in some year, you have to finish out the year or the semester or something like that. You can't just drop out in the middle. And so that led these authors to think, well, maybe the time of the year that you were born is going to affect, in a fairly arbitrary way, how much schooling you receive. So people who are born in like January are more likely to start first grade sooner and turn 16 sooner than someone who's born in December. And so that creates a little bit of fairly arbitrary variation in how much schooling somebody gets, which arguably is an instrument, although it doesn't seem to be a particularly strong one. And so if we estimate this using the frequentist function in the AER package, you just do it like this, and you get a point estimate of the average of the causal effect of not dropping out of school to be 0.13 almost. And this is with the outcome as being the log of wages. So that can be interpreted kind of like a 13% increase at the point estimate in wages, which sounds pretty big. It sounds really big, really. But if you look at the p-value, is 0.0587. No stars, just a dot. And so conventional frequentist practice would say, well, you failed to reject the null hypothesis that the causal effect of schooling is 0. Therefore, proceed as if the causal effect is 0. Now, this is a rather absurd convention, and it's not even frequentist. Like, I make fun of Fisher all semester, but you can't really make fun of Fisher for this, because even he said this was dumb. Because it's a dumb procedure to say, well, if I fail to reject the null hypothesis as 0, I'm going to proceed as if it's 0. But if the p-value were like slightly below 0.05 rather than slightly above 0.05, then I'm going to proceed as if the effect of schooling is 0.13. So we like jumping from 0 to 0.13 based on is like the p-value above or below this 0.05 threshold. Like Fisher was not an advocate of that. Neither was Neyman. No one really was. Journals just kind of made this up because they needed a procedure to decide what papers to publish and what not. So another kind of absurd thing about this convention is a typical frequentist thing to do would be to say, wait, theory suggests that the more schooling you have, the more wages you should be. So we shouldn't do a two-tailed test of the null hypothesis that the coefficient is 0 against the alternative hypothesis that it's not 0. We should do a one-tailed test of the null hypothesis that it's 0 against the alternative hypothesis that it's positive, in which case we do reject the null hypothesis for a one-tailed test because this p-value is less than 0.1, in which case we're allowed to proceed as if the point estimate is true and the point estimate is 0.13, which is a huge return to an additional year of schooling. It's probably too huge a return to additional year of schooling. This is another situation where we're talking about like a local average treatment effect. So this is not even like you get enough schooling to graduate from high school. This is like, what if you're a sophomore and you're not allowed to drop out because your birthday didn't quite come before the deadline? So you have to like finish your sophomore year instead of dropping out at the end of your sophomore year or something like that. So we're talking about an intermediate year of high school that you get extra depending on when your birthday comes. And if you think about, someone in that situation that like wanted to drop out after their sophomore year, but they couldn't, so they had to stick around for their junior year, how much learning is someone like that really gonna do? Now, maybe in that extra year they discover they really love biology and they go on to make a career in biology. Or maybe in that extra year they just start to grow up and like get their act together. Maybe in that extra year they finally get the right medication dosage or whatever, and they can, deal with life or whatever. But for the most part, we're talking about somebody who doesn't want to be in school anyway. How could they get a return on this that's like double the return of a stock market, on average, which is like 6.5%? It sounds too big. Also, if we were to construct a 95% confidence interval and misinterpret that as a credible interval, well, the standard error here is about 0.07. So the 95% confidence interval will be essentially 0.13 plus or minus 14.14. So pretty much ranging from negative 0.01 to positive 0.25. And so if we were to misinterpret this as like asymptotically normal Bayesian posterior distribution and say, okay, like we're not too concerned about the point estimate, the interval estimate says, okay, this is somewhere between 0 and 0.25, which is no really different from saying this is a real number. Like the return on investment somewhere between 0 and 25%. That is basically saying this could be anything, which is to say we don't know what it is. But this is despite having conditioned on like 60,000 or something observations or whatever in this data set and coming out with like a fake posterior distribution that is way worse than anyone's prior. Like if you talk to economists and say like, what do you think the return to schooling is for somebody who has to stay an extra year of high school but doesn't really want to be there? They would say, well, it's probably on the low end of, other human capital investments, and we, kind of have an idea what those are. So maybe like 5% or something like that might be a reasonable estimate. And, we're coming back with something that's like way worse than that using frequentist methods. But we could do Bayesian methods. Moreover, if we have the theory that the instrument is monotonically related to the treatment variable, we can just do that. We learned how to do that 2 weeks ago. Can just do it in BRM. Got to defend that assumption, but you have to do that anyway. So you might as well put that into your estimator. Got some other stuff going on, including this LKJ prior on the residual correlation. So what does that mean? A lot of people think I invented the LKJ distribution. That is totally not true. If I invented the LKJ distribution, I would not have named it like the LKJ distribution. But I did come up with that abbreviation, which was not something clever on my part. This is based on a paper by 3 authors whose names are Lewandowski, Kurafishka, and Joe. But I could never remember how to spell Lewandowski or Kurafishka, so I just said, we're going to call this LKJ. So really my only contribution to this is I made up the abbreviation to a distribution that these 3 people came up with. They are not Bayesian, so I also recognized how useful this would be as a prior over correlation matrices, which allows you to separate the correlations from the standard deviations. So remember, a covariance is correlation between 2 things times the standard deviation of the first thing times the standard deviation of the second thing. When we do this Bayesian stuff, we like to separate those 3 things out because it makes it easier for us to think about priors. Also, it is almost always the case that the correlation doesn't tell you anything about the standard deviation or vice versa, because correlations are designed to be unit free. So like if somebody told you, oh, the correlation between these 2 things is 0.25, would that tell you anything about their variances? No. So it's reasonable to model those as independent, which is what we tend to do when doing stuff with Stan. And BRMS supports that. So main thing to know is that this shape parameter that goes into the LKJ, if it's 1, then the density is going to be flat over the space of correlation matrices. If it, to the extent that it's greater than 1, the PDF is kind of going to be upside down U-shaped, centered on 0 for all the correlations. And so you can have a sort of weakly informative prior that you don't think the correlations are too far away from 0, which is usually a pretty reasonable thing to think about error terms. So we could have priors for this. Because there's 2 outcome variables, like log wages and schooling, that are being modeled, we have to specify the RESP argument to indicate what part of the model we're talking about, which we haven't had to do before, but it's not particularly hard. We see here that I'm specifying the coefficient on birth quarter on the log wage part of the model to be the constant 0. So not a random variable, which is the exclusion restriction thing in an instrumental variables model. But I can put, a regular monotonic prior on the scale thing in the schooling part of the model. So I did like 0.01 with a standard deviation 0.05 because I didn't think it would be that big. And then, regular priors on the intercepts of these 2 things. So like 12 years would be kind of normal for schooling. And then the sigmas. And then I did LKJ 1.5 on the error correlation of those 2 things. So weakly informative toward 0. And then we could do that, get the posterior distribution. Posterior distribution. So takes a while, but it's not difficult to specify. And then once we get the draws of sigma for log wage, sigma for schooling, and the residual correlation between those 2 things, we can combine those all together to get a posterior distribution of delta, which is the average causal effect. And that posterior density looks like this. So we get a posterior median around 0.068. And the whole plot ranges from 0.065 to 0.073. So what have we done here? pretty much regular Bayesian stuff, same Stan, MCMC. We had some informative priors, but the informative priors were basically the same things you have to believe in order to do the frequentist version of the estimator. The exclusion restriction being valid, monotonic relationship between the instrument and the treatment variable. So pretty much the same thing. It's a little bit stronger because we assumed the errors were normal, but that is still like a fairly germane thing. And we got a posterior distribution that is extremely concentrated around a fairly reasonable value for the treatment effect, closer to maybe a little bit less than 7%, as opposed to the point estimate from two-stage least squares, which was 13%, with a 95% confidence interval anywhere between 0 and 0.25, which is useless. And we got a 95% credible interval. It's like between 0.65, or really between like probably 0.066 and 0.07 would be like 95% of this. So we condition on 60,000 observations with the priors and all that stuff, and we get a very precise estimate and reasonable for this thing. Whereas if you do the frequentist thing, you get this like marginally significant, very uncertain point estimate that's very noisy, not very useful thing, because the instrument in this case is so weak that the estimator is real noisy. And we can combat that in a variety of ways, but part of it, combating that, is having the assumption that there's a monotonic relationship between the quarter of your birth and how much schooling you get before you drop out. So that's part of it, but also having priors on the standard deviations and all that stuff helps. So this is, I would say, a much better estimate of the causal effect of not dropping out of school until 1 year later than the frequentist estimate. Now, the authors of the paper were aware of this problem, and since like 1991, there's been a lot of research about how bad weak instruments could be, and they suggest all these like various pretty much frequentist things. But one thing they, of course, don't suggest is just use the Bayesian estimator and do your thing, and you don't really have these problems. So that, I think, is a pretty important thing, as is McElreath's general statements about hierarchical models. So McElreath comes out and says, at the beginning of the book, at the end of the book, hierarchical models should be the default. You need a strong theoretical and even stronger empirical reason to not use a hierarchical model, which have several advantages. You get better estimates if you have like repeat sampling on the same people. You get better estimates when some part of your sample is overrepresented and another part of your sample is underrepresented. You get estimates of uncertainty or variation from MCMC, and you avoid premature averaging. And so you can propagate your uncertainty about the parameters through to the quantities of interest, through to the predictions, etc. And McElreath thinks it, but he doesn't say it so strongly, is that maximum likelihood is a terrible estimator of hierarchical models because it doesn't utilize the fact that you can use prior information to say, well, I think there's going to be some heterogeneity, but it's unlikely for there to be a huge amount of heterogeneity across big units or whatever. Also, if you use MCMC, then basically for free, you get these uncertainty intervals and whatnot. You can propagate those through. And particularly when you get into hierarchical models, the 95% confidence intervals and stuff like that, the maximum likelihood produce, stop corresponding particularly well to 95% credible intervals that an actual Bayesian procedure yields. Also, if you do a hierarchical model that is like more complicated than just, okay, the intercept varies randomly across big units, like that one is simple enough that maximum likelihood is like, it's not as good as Bayes, but it's not like totally terrible. But if you start to do hierarchical models that are more complicated than just like random intercept across big units, the maximum likelihood is often going to yield an estimator on the boundary of the parameter space. So either say like some sigma is 0 or some correlation is either +1 or -1. So all the way on the boundary of the admissible space. And if that happens, the maximum likelihood estimator is like not really justifiable. But the Bayesian estimator, like I said a couple of times, we're not too concerned about the mode. So the mode, particularly if you don't have strong prior information, may very well be on the boundary of the parameter space. But the median is in the interior of the parameter space. The mean is in the interior parameter space. Every single one of the 4,000 draws is in the interior of the parameter space. It's just the mode might be on the edge. And so the Bayesian thing yields like, or it can yield, perfectly good posteriors when the maximum likelihood estimator is on the boundary of the parameter space, which really invalidates the maximum likelihood estimator in the first place. Another reason why McElreath favors hierarchical models, thinks they should be default way of proceeding, is that it sort of navigates between underfitting and overfitting. So if you estimate a model which says there's like no heterogeneity across big units, then that will typically underfit the data because it fails to take into account said heterogeneity that you assume is not there. But if you estimate like a model for New York and do like no pooling at all, and estimate a model for Connecticut, not taking into account that the parameters for New York and the parameters for Connecticut, although they might not be totally identical, probably are not going to be too different. You can get wildly different estimates for New York than you get for Connecticut, which doesn't really make sense. And that is said to be a no pooling model, and those are going to tend to overfit the data because you're not telling them, well, these two states are pretty similar. I would not expect the parameters governing the data generating process to be too different between them. Whereas hierarchical models do partial pooling, so they allow some amount of heterogeneity, and they allow you to estimate how much heterogeneity there is. You have to have a prior about that, but you can get updated posterior beliefs about that, and your posterior distribution allows you to marginalize over the remaining uncertainty. So sure, let's do this. Okay, so we've done this example a couple times in recitation about the wells in Bangladesh that are contaminated by arsenic. So it could estimate a spline that has two inputs to it. So this is a bivariate spline on the amount of poison and how far is the nearest safe well. And the outcome variable is, does the person switch from the poisoned well to the safe well? And then we also have another variable like, is the person part of a neighborhood association? So this is a model that's like not so difficult to estimate in BRMS. It would be a disaster in frequentist, but we're not going to do that. So you might ask, can we obtain some subset of this larger model that has almost the same expected log predictive density, but uses fewer predictors? Now, it's not going to have exactly the same ELPD. It'll be a little bit worse. But maybe it's only a tiny bit worse. And if you had some external reason to prefer a model with fewer predictors, then maybe you could justify that. So what might those reasons be? Well, what if one of your predictors was really expensive to collect data on? Could you get away with not including it in your model? Or, some other reason, maybe your audience can't deal with a spline. So, could we estimate a simpler model that would be almost as good, but not have as many predictors in it? And that can, in fact, be done. But you want to use the ProjPred package, which is on CRAN, so you have to install it. Also, I forgot to put this on there. You should reinstall the LME4 and the Matrix package from CRAN to make sure you have the latest versions of those. Otherwise, there can be a problem with some things in BRMS. But anyway, the ProjPred package is the correct way to try to find a simplified model. So you might think, well, I'll just take stuff out of the model and see how ELPD changes. That's technically not right, because if you take stuff out, you're basically conditioning on that coefficient being exactly 0. But if you leave it in, you're not sure if it's exactly 0. You can look at the posterior distribution. It's like kind of centered around 0 maybe. But you still have posterior uncertainty as to whether it's exactly 0. And so what the ProjPred package does is it retains the original uncertainty, but incorporates it into the predictions from a submodel of the big model. So you still get the right uncertainty, even though you're getting a simpler model. And so there's a varcel or a CV varcel function in the ProjPred package that you can call. It makes this object, and then when you plot it, you can see, okay, here's like the maximum ELPD that can be achieved with the full model, and then what's the difference in the ELPD for various submodels. If I take into account, I'm not sure that the stuff I'm taking out has a coefficient of 0. I have posterior uncertainty about that fact from the original model. So if you go with the simplest possible model, in this case, just the intercept, the ELPD goes way down. So that's not good. But that's the simplest possible model. If you add the intercept and the bivariate spline, the ELPD jumps up to almost a difference of 0. And then it pretty much stays at the same thing if you were to add are you part of a neighborhood association variable? And then if you were to add as linear pieces the arsenic and the distance to the closest well. So this would say model number 1 is simpler and almost as good, dropping out the association variable from it. So if that was like expensive to collect data on, which I don't know why it would be, but if it was, you might justify a model that only had the bivariate spline, not any of the other stuff. And you can do, once you've decided which model you want to do, call these other functions, and it will make the sort of intermediate model, but retaining the original uncertainty about the effect of being in an association. So you don't get a bias by saying, oh, the effect of association is exactly 0, when you don't know that for a fact in your posterior distribution. Okay, so out of time, but need to mention the final exam. So you saw probably email from like the provost or whatever saying there needs to be an option to do the exam hybrid. So we're just going to do the final exam over Zoom for everybody. It will be May 9th from 7 to 10 in New York time. So you can be anywhere in the world. But the exam is happening at 7 to 10 New York time, but you don't have to come into campus or even be in New York. We'll just do it over Zoom. Similar in format to the identical, really, but slightly longer in format to the midterm. And it's cumulative in the sense that like Bayesian is cumulative. So we've done a whole bunch of stuff since the midterm, but all of it is built on the framework we were building up prior to the midterm. So it's not like you can say, oh, I don't have to study probability because that was before the midterm or whatever. But we're still using probability for everything that we do. So it's not really like it's cumulative, but we're certainly going to have a lot of questions that we could ask about the stuff that we've done since spring break, but also tying what we've done after spring break to some of the ideas from before the spring break. So I think, you shouldn't really be surprised by any of the questions, but they are going to be some of them. It's going to involve code, and it's going to involve English explanation. It's going to involve making plots. A lot of the questions are going to be, well, what if you did something slightly different from what we've done before, but still in the same framework? And then, how would you proceed, with all that? Also, people ask me well, what would be the next class to take after this one? And also people they like to write on the evaluations oh, this class is great, it should be split over 3 semesters. So that's not gonna, logistically speaking, I would be happy for that, but that's not gonna happen. So part of the reason why we had to do this at the pace that we had to do it is because there kind of isn't there's no 5066 or whatever, which would be the continuation of this class. And in order to get to where we got the last couple weeks, where we start to do the stuff that really makes Bayesian analysis shine, and we start to see examples where the Bayesian answer is different and better than the frequentist answer or the supervised learning answer or whatever, that only started to show up these last couple weeks. And so in order to arrive at the last couple weeks on time, we had to go pretty quickly through probability and stuff. But there isn't exactly another class to take. There is Gelman's class that he teaches to graduate students mostly in the stat department, although it's open to other people. But he usually teaches that in the spring. And so those of you who are graduating in May or those of you who are graduating in December, it's not really an option to take that class. Gelman, for those of you who are going to be here in the fall, Gelman does teach a class. I'm not totally sure what it's going to be in the fall, which, because it's Gelman, is going to have a lot of Bayesian thinking to it, but it may not be exclusively Bayesian class.
I know he's not going to be teaching it next semester, but David Blaze,
right? Yeah. So
models, or whatever they call now, probabilistic machine learning.
Yes. So both Dave Bly and a guy in the EECS, Electrical Engineering and Computer Science school, named John Paisley, teach classes that have Bayesian and machine learning in the title. They don't appear to be teaching those in the fall. But if you Google them or go to their web pages, you can see the course notes from when they have taught those things in the past. And even though they have Bayesian in the title, they're actually fairly different from what we have done in this class. They're still Bayesian, but not Stan. And so you oftentimes learning how to code up your own estimator, usually not using MCMC, but maybe some other sort of estimator that's approximation to the posterior distribution or something like that. So in the past, third semester QMSS students have taken those classes and usually found them to be pretty challenging because of the coding and algorithm aspects to the homeworks, which are kind of second nature for data science students or stat department students that aren't really exactly germane to what QMSS does. So people have taken the classes, they've learned a lot of stuff, they've liked them, but they often find the coding of algorithms to be kind of like a bridge too far, and they're like, well, why don't we just use Stan? And in a lot of situations for data sets that are typical in the social science, like just use Stan would actually be way preferable to social scientists just writing their own algorithms, which would have all kinds of bugs and would probably be worse than what Stan is doing. So bottom line, I don't think there is a fall semester class that really extends on them. For those of you who might be here in the spring, there could be some stuff. Look on the catalog. But for most of you, particularly most of you in the QMSS, this is kind of it. But there's certainly all sorts of stuff on the internet of varying quality. So I put a bunch of books on the syllabus. I haven't actually read all of them, but based on the authors and like skimming the table of contents, I think they're all pretty good. And some of them get into what would be the next step if there was a next step. So what that next step would be starting to write your own code to draw from posterior distribution using the Stan language rather than using RStanArm where we wrote the models for you, or using BRMS, which like auto translates our syntax into Stan syntax and then does the thing. The next sort of skill that's beyond this class is learning the Stan language. Now the Stan language is not difficult. Like there's basically just two data types, like integers and real numbers, and then like containers thereof, like with a matrix or an array or something like that. So it's actually an easier language to learn than Python or R or any language really. We didn't do that because, well, if you don't know what you're doing, then doing it in Stan is difficult. So we sort of had to learn like what Bayesian inference is and like what MCMC is all about. Once you kind of appreciate that, then learning how to do it yourself in the Stan language is not so difficult. We said it, we maybe had one example. You pretty much just write the numerator of Bayes' rule in log units and give that to Stan, and you're good to go. So anyway, that would be the next step, but it's not like there's a class that can really get you to the next step. So that'd be something that you would maybe want to try to learn on your own, maybe this summer. I'll keep Ed discussion open, so if you want to ask some questions about that, we can continue to do that, but I don't really think there's a fall class that would piggyback on this, which is why we had to do so much of this now. So anyway, over time, no more recitations, because that's gonna Wednesday is like reading period, so you can't have recitation during that. I will have office hours this Tuesday and the Tuesday afterward, but then so you can sign up for those, and certainly up until the exam you can post more questions on a discussion. Somebody will get back to you on that, but I think that's all I can remember. And if I forgot something, then I'll put it on that discussion. So anyway, so I put a post about the GDP thing that happened this morning. Check that out. But other than that, I think that's plenty. So see you all around.